Today, what I hope to describe for you is the torque that is applied to a closed circuit loop which is rectangular in shape, in which there is a current flowing in the presence of a magnetic field, and what we hope to find, or what I hope to show you, is the torque that is applied to this closed loop in the presence of a magnetic field. So let me describe the loop a little bit to you. We have a rectangular loop whose length is B, and that's represented by sides 1 and sides 2. A length of A, which is represented by sides 2 and sides 4. So sides 2 and sides 4 are parallel with each other. Sides 1 and 3 are parallel with each other as well. We see that the current is traveling in a counterclockwise rotation. This purplish blue line represents the shaft on which this loop is going to rotate. The white arrow over here, or arrows, the 4 arrows over there, represents the magnetic field. They're going to represent the magnetic field. And a few things I want to note still about this left-hand side is that sides 1 and sides 3 are parallel with the magnetic field. Since they're parallel with the magnetic field we learned earlier, there is no force on those sides. So since the current is parallel with the magnetic field, there is not going to be a force applied to those sides. Now, that's different than sides 2 and sides 4. Sides 2 and sides 4 are perpendicular to the magnetic field, and thus there will be a force applied to those two sides. Now you may ask next, what is the direction of that force? Well, we're going to be using the right-hand rule to describe that. Remember, our fingers are going to point in the direction of the magnetic field. Our thumb is going to point in the direction of the current, and our palm is going to point in the direction of the magnetic force. So let's now look at this corner right here. Let's look at this corner right here, which would be the same as the corner down there. If we look at this corner up here, remembering that our fingers are going to point in the direction of the magnetic field, our thumb is going to point in the direction of the current, and our palm represents the direction of the magnetic force. So here, the force is going to be pointing out of the board and into the camera. If we look at sides 4 right here, all right, in this case, our fingers are going to point once again, so we're looking at this corner here, side 4. Our fingers are going to point in the direction of the magnetic field, and our thumb is going to point in the direction of the current, and our palm represents the direction of the force. If we do that here, what we see is that the force now is into the board. So on this side, the force is coming out at you. In this side, the force is going into the board, away from you. Now, let's take a bird's eye view of this loop. And that's what we have here on the right-hand side. So here is going to be this length right there, right? The length here is going to be represented by that length here. We're taking a bird's eye view down. The blue dot here is going to represent the shaft right here. This, as we concluded a few moments ago, is going to be coming out at you. So this dot represents is coming out at you. Over on side 4, this is going into the board. Now the force 2 and force 4, this is not going up and that's not going down. This represents that it's coming out at you. Force 4, it's going into the board. I didn't know how to draw this in 3 dimensions, let alone 4 dimensions. Forget about that. Here is going to be our magnetic field B. Okay. Now as we stated over here on the right-hand side, the force here that's parallel to B, there is not going to be a force when the current is parallel with B. If that were the case, if the force were this way, if the magnetic field was this way, then the force would be coming out towards you. So this whole loop is going to rotate this way. This side's coming out at you, this side's going into the board. Now ultimately what we said that we're trying to determine the torque. that is applied to this loop based on or because of the magnetic field. Now, we said that force 2 is equal to force 4. It's just opposite in direction, equal in magnitude. Because the length of side 2 and the length of side 4 are going to be the same. Therefore, the force here and the force there are going to be equal. All right. Now, as I stated, this length is this length right there. And so if we take half of it, that's going to be b over 2. Therefore, since the lengths 2 and 4 are equal, forces 2 and forces 4 are equal, and that's going to be equal to I, which is the current, A, which is going to be our length here, and B is going to be the strength of the magnetic field. So that's going to be our force. Now, if we go back to the previous semester, we talked a little bit about torque. And what torque is torque is going to be equal to, if we're not looking at the direction, we're simply just looking at the magnitude, the torque is going to be equal to the force times the radius or times the distance. That distance is typically going to be a radius because it's a rotational force. And so what we can do now is we can say that our torque is equal to our force times the radius or times the distance. This here happens to be the radius of the loop being rotated. Therefore, our force, our torque on this side is going to be equal to the force of 2 times the distance b over 2, because this entire length here is b, and so therefore from the midway point to the end is going to be b over 2. And likewise, the same thing with the force 4. If we're looking at the torque applied here, it's going to be force 4 times this length, which is b over 2. Therefore, the total torque in the entire system is going to be force 2, b over 2, plus force 4, b over 2 as well. Now, we just concluded previously, a little while ago, that the force due to the magnetic field is going to be the current times the length of A times the magnetic field B. Therefore, we can plug this into our force. Now, force 2 and force 4 are going to be equal to one another. And if we plug IAB in for our force 1 into our force 2 as well as our force 4, we're going to get twice I, which is current, A, which is the length of sides 2 and 4, times B, which is the strength of the magnetic field, times this distance here, which is going to be b over 2. The 2's will cancel, and what we end up getting is we get I, A, B, B. So that's what I have written down here. I is the current, A is going to be the length of sides 2 and 4, B is going to be the length of sides 1 and 3, and B, capital B, is going to be the strength of the magnetic field. Now, if you go back to this picture here, I'll get on this side. If you go back to the picture here, if you take the length of A times the length of B, you end up getting the area of this loop. Therefore, we can combine the length of A times the length of B to be the area. Now, the total torque on this system, on a rectangular shaped closed loop, is going to be the current times the length of, times the area of our rectangular coil or a rectangular closed circuit times the magnitude or the strength of the magnetic field. If you have any questions on this, feel free to contact me.